everybody, I am seeing a couple different things. I'm seeing people try P over Q, which you could have tried that, but there are no rational roots. So then you're like, well, then how do I solve it? So I wouldn't have even started with P over Q because I noticed this is a quadratic in form, correct? Yeah. We can make it's x fourth, x squared, and then a constant. So it kind of looks like x squared plus bx plus c, which is quadratic in form. So we would say let x squared be equal to u. So then we know we have 4 times x squared squared minus 11x squared minus 3. So we really have 4 times u squared. So we have 4u squared minus 11u minus 3. And now we'd say, how do we solve that? Well, we know how to solve a quadratic. Did it factor? Yeah. I would solve by factoring what multiplies to be 8 times c, what multiplies to be negative 12 and adds up to be negative 11. This is a highly missed problem on the test. 1 times 12, negative 12, correct? So this factors, oh, I can't quick factor it, so I got to drop down 4u squared, drop down the end terms, negative 3, break down the middle term as I'm going to strategically put negative 12 first. Is everybody okay with why I'm putting that first? Just because it divides by 4, it's going to be a little bit easier for me. So minus 12u and then plus 1u. Then we have 4 terms, so we'll factor by grouping, which a lot of people missed on the test as well. The greatest thing in common here is 4u. So then left would be u minus 3, correct? Pull out, don't say nothing. A lot of people said nothing on the test. There's always a 1 there. Left is u minus 3. We've factored it correctly. Because our safe haven's the same, we'll factor out u minus 3, we'll factor out 4u, and left is 4u plus 1. So now it was equal to 0. It was equal to 0, so it's still equal to 0. Set each equal to 0 and solve. So we get u is equal to 3 and u is equal to subtract 1 divided by 4, negative 1/4. So those are u's. So now let's figure out what x squared is. So we know x squared is equal to u, so x squared is equal to 3, and we know x squared is equal to u, which is negative 1/4. Solve for x, we would square root it. X is equal to plus and minus the square root of 3, right? There's 2 solutions. Over here we would square root it. So we have x is equal to, if we have a square root and the fraction doesn't simplify, we split it up. So on top we have the square root of on top, we have the square root of negative 1. On bottom, we have the square root of 4. So what's the square root of negative 1? The square root of 4 is 2. So we have plus and minus 2i, I over 2, right? Now, the fundamental theorem of algebra said we should have 4 solutions, and we do. So we've probably done it correctly as long as our math checks out. Anyway. Any questions? That was a highly missed problem on the test. All right. Here is what you have to know for the test. I have to give you homework this time, but we'll see how it goes. So 2-8 is just modeling polynomials in the real world. It's actually really easy because all we're doing is using our graphing calculator. There's really not a whole lot of math involved. It's just knowing how to use your calculator and type it in. So first of all, we know polynomial functions can be degree 0. We can have constant polynomials that can be degree 1. That would make it linear. Polynomials can be degree 2. That would make it quadratic. Degree 3, cubic, and so on. So you can use polynomial functions to model many real-world situations. The behavior of the graphs of polynomial functions of different degrees can suggest what type of polynomial will best fit a particular data set. So remember back to the lesson where we could figure out what degree this is by taking differences, correct? Yes, also, we could look at the graph, we could plot those points like in these. So these are the points plotted, that these XY points just plotted. Do you see how a line definitely doesn't match up the point? A line wouldn't be a good fit for this data set. Now this is a quadratic graph, but do you see how the points are not connected here? This is not a good model for this particular XY points. Now, if I draw in a cubic, do you see how it matches up with the points perfectly? Okay, so we would know that this is a cubic function. So everybody, I need your graphing calculator out. I'm going to show you how to get what cubic equation that is, what the exact equation is. So not only do we know it's cubic, but I'm going to show you how to actually get the actual equation. So pull up your graphing calculator, and you're going to hit the, everybody right here, stat key. Hit the stat key. Oh, one thing I want us to do first, quit, go out of there. What I want us to do first is actually, we need to turn on our statistics, our data statistics. So we're gonna all go second and then go down to 0 because see how it says catalog. We're gonna scroll down to the D's, which is we're gonna go to diagnostics, and we're gonna turn on our diagnostics. And I'll explain in a minute what that is. All right then, diagnostics on. So I'm gonna hit enter. And then I need to turn it on, so I hit enter again, and it says done. Okay, our diagnostics are turned on, so you shouldn't need to do that ever again. It should automatically stay on until you turn it off. So I think we're good, but you could turn it on if you needed to. Okay, now we're gonna hit the stat key. We're gonna go into edit. Hit enter. Everybody follow me, because if we don't have time to get lost. We hit the stat key. Then we hit enter into list 1 and list 2 and list 3. You can see the list. Does everybody say list 1, list 2 up here? If it says list 1, list 3, you've deleted a list on accident. That's bad. And this is what happens. I'm going to tell you right now what happens. People can't figure out why their equations are wrong or why it's saying error. And it's because they'll accidentally scroll up here and they're like trying to delete stuff out of their list and they'll hit like delete and it will get rid of the whole list. I don't know how to get it back. I just have to reset your calculator because I just haven't researched it enough. So if you do that, you'll have to reset your calculator, okay? So we need list 1 and list 2. In list 1, we're going to scroll down and we're going to put in our x values. So you're going to type in those x values. Let's see if I can scroll this over. I don't think so. I'm going to have to get out of here. So in list 1, you're typing in 0, enter, 5, enter, 10, enter, 15, enter, 20, enter. Now notice our x values are changing by the same amount each time, right? So we could take differences if we wanted, but anyways. Is everybody good with that? Did everybody do that? In list 2, so you'll scroll over. In list 2, you're going to type in your y values. Make sure they match up with the correct x values. That's what you're putting in list 2. If you have anything extra typed in, you're going to have, it's going to, when you go to calculate something, it's going to say error. Okay, awesome. So now what you're going to hit is the stat key again. You don't have to go anywhere else. You'll just hit the stat key again. And now we're going to go over to calculate. Now, if you look down here, we are going to calculate the linear regression line, the quadratic regression line, the cubic regression line. That means the cubic equation for this data set. So let's graph the linear one, and let's say we didn't know it was cubic. Let's graph the linear one and hit enter. So it says linear regression line, and you hit enter again. You get this screen. Now this is telling you that the lines have a form ax plus b, which we know. It's giving you the a value, and it's giving you the b value. So it's giving us an equation for those data points for a line. Now, this r squared is just, and we won't get into the gory details of it, but this is the percent perfectness it is to the points. It's a 55% accuracy. That's not accurate, guys, because it's not a line. So the closer this is to 1, the more perfect the graph, because that would be 100% accurate. So we know it's probably not a line. Does everybody understand? So we're going to hit stat again, go over to calculate, go down to quadratic regression line. Let's see if it's quadratic, or let's just calculate it for fun. So we have, it gives us an a value, a b value, a c value, and that's for ax squared plus bx plus c. And our r squared is 0.76. So it's more accurate than a line, 76% accurate. That's still very inaccurate. Everybody good with that? Okay, hit stat again, over to calculate. And then we go to cubic regression line. So if we would have taken our differences, we would have then had a constant at the third difference, and so we would have known it was cubic. But let me just show you. Cubic regression line, we get 0.999. That rounds to be 1, correct? So this is 100% accurate, or 0.99 accurate. It's very, very accurate. So this would be the actual equation. We would have this hideous thing, but that is the perfect fit for this equation. So if you do a lot of decimals, then we're not going to have pretty things. Because in the real world, they're not very pretty. They're not going to come out 3x cubed. You know what I mean? Anyway. Okay, do you guys see? All right, so let's do, oh yeah, one thing. So for any set of n plus 1 points in the coordinate plane that passes the vertical line test. So if we're given a couple points and we know that it's a function, meaning they pass the vertical line test, then there is a unique polynomial of degree at most n that fits the points perfectly. So if there's a polynomial of degree n that fits the points perfectly, isn't n plus 1 greater than the degree? Isn't n plus 1 greater than n, guys? So if we have 3 points, then there is a quadratic, isn't that less by 1, that fits those points perfectly. Okay? So this is called the n plus 1 point principle. So if we have 3 points that pass the vertical line test, then there's a quadratic that fits those 3 points perfectly. Does everybody get it? Yep. Okay, so let's do this problem. Just look real quick right here. It says, what polynomial function has a graph that passes through the 4 points? So we have 1, 2, 3, 4 points. So we have 4 points. So then that means that there's a cubic that matches those points perfectly, as long as they pass the vertical line test, and they do. Does that make sense? There's a cubic polynomial that matches those points perfectly. The n plus 1 point principle that we just learned. So if there's 5 points that pass the vertical line test, there's a 4th degree polynomial that matches the points. Does everybody understand? Yes. Yep, kind of, yes. So what we're going to do is go to Stat, Edit, in list 1, don't delete, just, oh, let me show you. Oh, annoying. I get like okay, on my phone. So in list 1, you'll type in your x values. So in list 1, you'll type in 0, 1, 2, and -1. In list 2, you'll type in the y values that correspond to those x values. So -3, -1, 5, and -7. I can't bring it up or else it covers your problem, which is annoying. You have to hit the delete key. You cannot use the clear key. Oh, it's opposite? Oh, I think clear does clear off just the piece, but you can use both. Just make sure you don't go up and delete on accident the list. Oh, interesting. Okay, so that's awesome because it would be nice to kind of clear out the whole list. I didn't know that. So if you hit, I didn't know that. So if you go to list and hit clear, you're okay. If you hit delete, it will delete the list. Does anyone have that? Then you hit stat again. Oh. But you can just reset your calculator. Okay, everybody, are we with me? Hit the stat key again. Go over to calculate. We decided it was cubic regression line. So what do we get? It equals 1. So it's 100% accurate. So tell me, what is the cubic? So we know a cubic has the form ax cubed plus bx squared plus cx plus d. What is a, b, and c, and d? So we have x cubed. What's b? So minus x squared plus 2x minus 3. Sweet. Yep. That is the cubic polynomial that matches both points. And it fits perfectly. Yes. So we could go through and do this by hand. Like, remember, I don't know if you remember back to the first assignment. I kind of had you doing some stuff like this. Anyway, but on just one of the advanced problems. But we would never again do it by hand because if we can use the technology, we can use that in the real world. So why not? Wait, so I put in like 0 and then 1. Here we go. So it says, find a polynomial function whose graph passes through each set of points. So we have 1, 2 points. So what kind of thing are we looking at? Linear, aligned. The n plus 1 point principle says that if you have n plus 1 points, then it's degree n. Isn't that 1 less than 1? I mean 1 less than n plus 1. So if there are 2 points, then it's degree 1, which is linear. Okay, sweet. So it's the same thing. In list 1, that, in list 2, that, and then stat, calculate linear regression line. Okay, we've got it. So lines have the form y is equal to ax plus b. What's a? Negative 2 x plus 7. Was r squared 1? Was 100% accurate. Let's do number 8. You got it? Yeah. Okay, awesome. So this is a what degree polynomial? Cubic, because it's 1 less than how many points we have. So it's cubic, and the cubic is, you got y is equal to, and then we have x cubed minus 2x squared plus 6x plus 9, and r squared was 1, so we knew it was a perfect fit. Sweet. So let's think a little bit critically here. If I said to you, okay, well, what's the function going to be at 4? Wouldn't you just plug in 4? Right? Into the equation? Right? Okay, that's how high up to go, right? Everybody? You know what I'm saying? So now I can find any xy point for this data set. Sweet. Okay, do 1 through 8. Ready, set, go. So let's go through it. So it says, let's read the instructions on the second part. It says, find a polynomial function that best models each set of values. So we could take differences, or really we could just quickly put this into list 1, and then list into list 2. But before you do that, just wait. And then calculate each of them. And then whatever one's r squared is closer to 1, use. Right? Yeah, so we got to read the instructions. It says, let x be the number of years after 1985. So x be the number of years after 1985. So how many years after 1985 is 1985? 0. How about that? 5, 10, 15. So in x, you got to type in 0, 5, 10, 15. And then in list 2, type in the 49.3, 70.2, 71.8, and 82.6. Okay, awesome. So you calculated cubic, and that is perfect fit because r squared was 1. So then you get y is equal to 0.038 x cubed minus 0.956x squared plus 8.01 x, and then plus 49.3. These are actually used in the real world. If you're hired as a statistician, you're going to be doing these stats, come up with an equation, because Vivint might say to you, what do you see our projected growth at year, or what do you see our cells at in 2013? You'd have to come up with something like this in the real world. So anyway, statisticians will use this. Okay, everybody got that? Everybody understanding? I want you to flip to the second page and read it, number 15. It says on 15, estimate world gold production. Are you listening? Estimate world gold production for years 2010. Sorry, 2000. What in the heavens? For years 2010 and 2020 and 2025. So, won't I just plug in? Can't I plug in any value for x and get what we're going to get out? Right? Does everybody understand that? If I want to know, like this is input output, right, everybody? So if I want to know how much we're going to have in year 2010, then I got to put in that for x. Now we got to put in the correct x. So how many years is 2010 after 1985? Guys, 2010 minus 1985. 25. Yep. So we have x is equal to 25, right? So we'll plug that in. We're going to get something out when we plug that in. So we have 0.038 times 25 cubed minus 0.956 times 25 squared plus 8.01 times 25 and then plus 49.3. Calculate it. Now your answer should make sense. It shouldn't be some outrageous thing or you know you've typed it in wrong or something. I mean, it should come out pretty similar to these. You know what I mean? You get what I'm saying? Okay, go. Calculate it. Everybody calculate it. Type it in. Answer? Nobody has it yet? What is it? 245 point. Did other people get that? Sweet, then I believe you. Awesome. So the production will be 245.8 troy ounces. So once again, if we wanted to do 2020, that's 35 years after 1985. So we'd plug in x is equal to 35. Do we get the gist of it? It's the same thing, just a different year. No, I'm gonna say if we understand it, we're good because it's such an easy assignment. Are we good? Yeah. Okay, then all I want you to do now is okay, so just answer these problems. I think you're understanding it. It says find a cubic and quadratic model for each set of values, then determine which best represents the value. Now you just look at our squares. Whichever one's closer to 1. You get what I'm saying? Nope. So we're good. Like literally we have learned everything that we need to learn, except for this one last wording. So I have literally never seen this till this year. It's just some quick wording in case you were to ever see it in the future. It's just some vocabulary. So interpolation versus extrapolation. So when just like I gave you the example for like the gold example. Okay, so let me give you an example here. We were able to come up with a polynomial for this data set, correct? Now, if we use that to calculate a different year for this same thing, that would be called interpolation because it's within the domain of the data set, meaning like the x we were plugging in makes sense. It's for the same company. It's, you know what I mean? Does that make sense? Like the company is showing this polynomial, and so if we use this to calculate a different year, it's interpolation because the domain is appropriate for the data set. So, but if I said to you, okay, what about a different company? Could we plug that in? Could we plug in and calculate something? Probably not, because that wouldn't be accurate for that company. That's extrapolation, meaning, so I'll just read the little part to you because they can say it better than me. But so it says, using a model to predict a y value outside of the domain of a data set is extrapolation, like x as in outside. Estimating within the domain is interpolation. So interpolation usually yields reliable estimates, and extrapolation becomes less reliable as you move further away from the data set. So I just gave an example. If a polynomial is modeling the sales records for a phone company at Verizon, and you use that polynomial to estimate sales for Verizon in the future, then that would be interpolation because the domain would work. It'd be the same. But if you use that polynomial to model sales records for a Sprint, then that's extrapolation because Sprint isn't the same as Verizon. I mean, since we've moved further away from the domain. So it's not too intense. That's the first time I've seen it. Making this lesson, yes. All right, so I'm not going to have you do all of the worksheet, but